Good afternoon, everyone. My name is Alexandre Pombo, and today we are going to talk about the spectral decomposition of Kerr black holes. Observe that this is still an ongoing work. Now, in an attempt to explain the observed universe, it is tentative to connect the dark matter phenomenon with the nearly observational data, as it is the case of the LIGO collaboration or the eventualized telescope data, either through the study of ultra-compact objects, namely boson stars, or the study of alternative black hole models. One of the most interesting cases occurs when the Kerr black hole is surrounded by a massive complex scalar field, which are known as Kerr black holes with scalar air, whose intricacies has long eliminated further developments. So, to get a better insight into the structure and the properties of this data, we propose to decompose the characteristic functions into the spherical harmonic spaces. This spherical harmonic decomposition is able to separate both the radial and angular variables, and is a widely known technique to solve PDEs, since it transforms PDEs into a couple of ODEs. However, what we propose is the retrograded process. Solutions are computed numerically and are a posteriori decomposed. A kind of spectroscopic analysis, and has the name of spectral decomposition. So, our main objective on this presentation is to study if the spectral decomposition is able to correctly describe the solutions and how many modes are necessary to correctly describe it. A kind of first-step analysis into a more interesting and in-depth study. So, let us start by studying the Kerr black holes. For this, I would like to thank Professor Kerr and Eugene Brado, who have given valuable discussions and several numerical data. Now, the action that describes a massive complex scalar field that is minimally coupled to the Einstein gravity comes as follows, where to solve the numerical equations, one has to propose suitable ansatz for the metric. For this, we will use the metric ansatz, a standard metric ansatz that is known to be used in numerical relativity. For the scalar field, we consider a scalar field that contains a time and azimuthal harmonic dependence, meaning that we have 5 different functions that require decomposition. The resulting solution is a spinning black hole that has synchronized scalar field. Now, what is left is for us to introduce the spectral decomposition. Let us start with the scalar field. For the case of the scalar field, it is symmetric under reflection in the equatorial plane, and has a well-defined parity. For concerning the spherical harmonics, they are described by associated Legendre functions, which also have a well-defined parity with respect to the same equatorial plane. So, when the spectral decomposition is performed, it will only contain terms with the same parity, since the terms with the different parity will cancel out. So, for a scalar field, an even scalar field, since we have the freedom to choose if the scalar field is even or odd, we will choose it even, with m equals to 1, the spectral decomposition can be given as a sum of several spectral modes, where the function f is the radial dependence of the scalar field for a given mode 2k plus 1, that multiplies by the associated Legendre function. This radial function can be obtained by projecting the scalar field into the spherical harmonic spaces. Concerning the metric functions, we observe that all the metric functions possess the same symmetry. They have an axial symmetry with m equals to 0, and are even with respect to the equatorial plane. So this means that due to the well-defined parity of the associated Legendre functions, only the even parity terms appears, and the generic spectral expansion for a generic metric function comes as a sum of the spectral function k for a given metric function I times an even parity associated Legendre function, where again this radial spectral function k is obtained by projecting the spectral function in the associated Legendre function basis. So, what is left is for us to perform some tests. Now, let us consider 5 different tests. First, to solely test the scalar field decomposition, let us consider the Komar mass, or in other words, the mass associated with the scalar field and the Noether charge, while keeping both the metric functions untouched. For the metric functions, let us consider 2 geometric quantities, the position of the light ring and the position of the icicle, which are both 2 quantities that are not explicitly dependent on the scalar field. To test the entire decomposition, we'll consider the virial additivity, whose computation is too complex to be here, but can be seen in our work, virial decomposition work. At last, I would like to introduce the relative error that will allow us to quantify the accuracy of our decomposition. This is just the ratio between the solution obtained by the spectral decomposition over the solution that is full, or in other words, that is untouched. For this, let us consider an exemplary solution that is close to the main branch of the spinning boson stars. But first, before the quantitative tests, let us do a qualitative test. For this, let us consider a scalar field at the equatorial plane, and we'll plot its radial dependence. We can see that the first spectral mode is the leading contributor for the shape of the scalar field, being followed by the second. If we do the same study for one exemplar metric function, in this case f0, we observe the same behavior. The first spectral mode, k0, is the leading contributor for the shape of the metric function, being followed by the second, while the third spectral mode is almost negligible. Now, concerning the quantitative tests, we observe that the first spectral mode contains almost 95% of the contribution for a given quantity. And if we add further spectral modes, we see a tendency of the solutions to go to the full solution. While for the fourth spectral mode, we almost reach the numerical accuracy. In addition, I would like also to point out that the case of the error of icicle contains the largest relative error, because it contains second derivatives, which due to our numerical process will introduce a lot of noise, which gives a high relative error. At last, I would like to introduce this decomposition and apply it to some cases. For this, let us consider a set of solutions that continuously connect between a Kerr black hole without scalar error to a spinning boson star. In other words, we'll start with a Kerr black hole and start to increase the air until we do not have any more black holes and only have the air, in other words, the spinning boson star. What we observe is that for a Kerr black hole that has a negligibly small amount of air, the scalar field is almost purely described by a single mode. And as we decrease the size of the horizon, or in other words, increase the impact of the scalar field, we see an increase in the impact of the higher modes, in particular, the increase in the second spectral mode impact. So, what do we conclude? First, we observe that in this work, we have done a preliminary study in the decomposition of Kerr black holes with scalar error into the spherical harmonic spaces. In this case, the well-defined parity of each spectral harmonics extremely simplifies the process. One has observed also that the difficulty to reproduce differential quantities, as the case of our icicle, but this seems to be just a numerical artifact. Concerning the structure of the solutions, we have observed that the first spectral mode is always the leading contributor, with almost 95%, being followed by the second and the third, while the fourth is almost negligible and can be just used for numerical accuracy. So, we have observed that the spectral decomposition is able to correctly decompose the set of solutions, can give us a precious insight into the structure of such solutions, which can open the door for future more complex studies. Thank you.